this lesson, we're going to talk about something called free body diagrams. And free body diagrams are relatively simplistic diagrams that we're going to be using that are going to actually display all of the forces that we are dealing with at any one time. We've talked about Newton's laws. So we know about his first law of inertia, the second law, F equals ma, and the third law, the action-reaction pairs. So in this concept, we want to take this one step further. And we want to start looking at how all these forces act together on a body. And if we recall, Newton's second law said that the net force, F net, was equal to ma. So this is going to give us a pictorial way to look at all these net forces. So what do I mean by pictorial? Well, let's start off with a simple scenario here. We have a 50-kilogram person standing on the floor. And you'll see why I'm a physics teacher and not an art teacher right now. But this person is just standing on the floor. They're not being pushed through the floor. They're not being shot into space. So we know we've got some forces that are acting on this, or on this person, because of Newton's laws. And the first one we're going to deal with will be their weight. So the force of gravity, which is their weight, and we can calculate this by using mg, a version of F equals ma. Now, if this was the only force that was acting on this person, they would be crushed down into the floor, and that's where this problem would stop. But we all have had the experience where we've been able to stand on a floor, we're not getting crushed into it. Why? The floor is exerting a force back to hold us up. And we call that the normal force. It is the supporting force. At the exact time here, in this scenario, we notice that there is no motion left or right. It's just up and down right now are the only forces we're considering. So let's take a look now at our free body diagram, which we've got here, and how that applies to this. Well, we're going to have the sum of the forces. I'm going to use y to represent the vertical up and down direction. And I know that has to equal ma, and I'm going to put a y there just so I know that that's also in the vertical direction. And we know that the sum of the forces are these forces here. So we're going to have a positive Fn and our gravitational force is going down. So I'm going to use a negative sign there. I'm going to do that in green. To show that it actually goes with the gravitational force. Now, as I started off by saying, this person is not moving up or down. They're stationary. Therefore, their acceleration is 0. Which means that this whole term goes to 0. So in our case that we've got here, our setup, we can do a little bit of arithmetic, and we find that Fn is going to equal Fg. Now, this doesn't mean that the vectors themselves are the same. the magnitudes are the same. We know that this negative sign tells me that the gravitational force is going down. All right. So this gives us a way we can find the normal force that's applied in this given situation. So let's actually go through and solve this. We know that Fg is equal to mg. And according to the problem here, m is 50 kilograms. So I'm going to have 50 kilograms. Gravity, 9.81 meters per second squared. Multiplying these together, we're going to find that we get a force of 491 newtons. So that is the weight of this person on a flat floor. Now we're going to take a few minutes and we're going to take a look at how this applies to an elevator problem. In an elevator problem, we are frequently given a situation where we have a person standing in the elevator and the elevator moves. And they want us to tell what value the scale that this person is standing on in the elevator reads. Now, first of all, why are they standing on a scale in an elevator? I don't know. Okay, most people I know don't want to stand on a scale anywhere. But for this reason, or for this problems, they're standing on a scale in the elevator. So we've got a 50 kilogram person standing on the scale. What does the scale read when they're at rest? When they're accelerating upward at 1 meter per second squared, and when they accelerate downward at 1 meter per second squared. So the first thing we're going to do is we're going to actually draw our free body diagram. So I'm not going to draw the actual elevator car, but there's the scale the person's going to stand on. And there's my 50 kilogram person. Now we can start by looking at what forces we know are acting on this person. All right. So there's our free body diagram. Again, just a quick picture of all the forces that are acting on this person at one time. So in this particular setup, we're going to look at the first part, at rest. Now we've already done this exact problem. Go back to the beginning of the video. We just actually did this, okay? We are looking at a person, 50 kilograms, standing on an object, and we know that there's no acceleration up or down. They're standing still. Therefore, this is going to come out at 491 newtons. Okay, so now let's take a look at how we would do the next two parts here. So for part B, all right, we're going to look at the sum of the forces in the y direction, and we know they have to equal the mass times acceleration in a y direction. And those forces that we're going to be encountering here, we're going to have a negative Fg, gravity is always going down, and we're going to have a positive Fn. So what we're going to do now is we're going to solve this problem. All right, a little bit of manipulation here, and I'm going to add a couple of variables in. All right, so we're going to have mass times acceleration in the y direction equals. We know that Fg is going to be minus mass times gravity, plus Fn. Now, to think about our problem here, what we have to do is we've got to figure out what is Fn going to actually read. Okay, that's what we're going to have to solve for here. Why? It's the supporting force that the person is undergoing. So in order for us to solve this problem, we have to solve for Fn. That's what we're going to be looking for. All right. So to find Fn, what I'm going to do is I'm going to get rid of this on this side. We're going to move it over. And to do that, of course, we have to add mg to both sides. So now I've got MAY plus mg equals Fn. So this is the equation I'm going to be using to actually figure out what Fn is going to equal. Now, I'm going to do a little bit of manipulation here. Straight algebra. I have a mass and a mass. These are both the same masses, aren't they? I can pull them out. So I have the mass times the acceleration of the y direction plus gravity. Equals my normal force. Okay. 50.0 kilograms given to me in my problem times AY, we said was 1 meter per second going up, gravity 9.81. And that'll equal Fn. Now, according to math, I have to do what's in my parentheses first. So this is really going to come out at 50.0 kilograms times 10.81 meters per second squared. And we do the multiplication here, we get 540 newtons is what the scale is going to read. Okay? Does it make sense? We've all been in elevators. When the elevator starts going up, we feel like we're going down. We feel the compression, right? We feel that extra weight. We feel heavier. Did we get heavier? Yep. That's what the scale shows us. We got a little bit heavier. Now for part C, I'm not going to go back and totally reinvent the wheel. We're going to leave the equation we started with for B, and we're going to see it's really the same equation. All right, we're going to have the sum of the forces in the y direction has to equal the mass times acceleration in the y direction it's going to equal a negative gravity and a positive normal force. Exactly what we had the last time. So what I'm going to do is I'm just going to kind of jump to that step here where we've actually got the algebra done. And what that's going to give us now is we're going to have the mass times the acceleration in the y direction plus g equals Fn. All right, let's put some numbers in here. So our mass is still 50 kilograms. The acceleration in the y direction. In this case, because the elevator is accelerating downward, our acceleration then is going to be negative 1.00 meters per second squared plus our 9.81 meters per second squared. Oops. 50.0 kilograms. This is going to give me now 8.81 meters per second squared. Okay, so we've got 50.0 kilograms times 8.81 meters per second squared equals Fn. Do the math here, we get this is going to come out at 440.5 newtons. Because we have 3 significant digits, we're going to express this as 441 newtons. And again, look at the answers. Do they make sense? We know that we feel lighter when the bottom drops out on us, and we definitely look to be lighter there.